Hello dear student, I am Monroe Islam. Today in this video we are going to discuss an important topic, that is Holder continous. Okay, we are now studying about Holder continous of a function. What is Holder continous? When we say a function is Holder continous. Okay, so this is definition. If suppose f be a real valued function, then we say f is Holder continuous with exponent alpha belongs to open 0 close 1. If there is this number c greater 0 such that mod of fs minus fy less than equal to c into mod of x minus y whole to alpha for x belongs to domain f. If this condition is satisfied, then we say the function f is Holder continuous with exponent alpha, where alpha lies between open 0 close 1. Okay, so see, and using this we are now solving 5. There are 1 2 3 property. Okay, first property, second property, third property, one by one we will do, and next we solve a problem of Nbhm PhD. Okay, so please see the video to the end. Okay, so suppose we have a function f from R to R. Okay, we have function f from R to R. Then f is said to be Holder continuous. Okay, I am writing it in short form. If there is positive constant, suppose m greater 0, such that mod of fx minus fy, this can be made less than m into mod x minus y whole power alpha. Okay, for all xy belongs to R. This R is nothing but डोमेन of f. ये जो मैपिंग है ना f का, इसका डोमेन है फॉर एक्स वाई बिलोंग्स टू R, where R is domain of f. So what is the definition of Holder continuous function? A function f from R to R is said to be a real function. Means if we take x from here, then we have fx from here, fx goes R. Okay, so this is a real root function. A real root function f from R to R is said to be Holder continuous of exponent alpha if there is a constant, there is a opposite constant m greater 0 such that this condition hold. Fs minus fy less than equal to mod of x minus y whole to alpha, where for x belongs to domain of f. Okay, now then we say that the function f is Holder continuous. Holder continuous. Okay, on R. Now this alpha is a real number. Okay, alpha is a real number, and this alpha must be positive. I have to mention in this side alpha should be positive. The exponent should be always positive. Okay, it never negative, because if it's negative then it will, if it's minus 1 then it will become m into 1 upon mod x minus y. Okay, and if x equal y, then this part goes to infinity. Okay, so alpha should be always positive, alpha never negative. So first observation, alpha is always positive. Okay, and alpha always lies between 0 and 1. Okay, alpha should be lies between this, or alpha may be greater than 1. Okay, because alpha is a real number which is positive, so two cases. Okay, either alpha will lie be 0 open 0 close 1, or alpha may be greater than 1. Okay, now we show that if alpha greater than 1, the only function satisfying this condition is identically constant. Okay, if alpha greater than 1, the only function satisfying this condition is constant. So for a non-constant function we must have 0 less than alpha less than mod 1. For a non-constant function we must have 0 less than alpha less equal to 1. Okay, See how this happen. See, first take alpha greater than 1. Okay, I am choosing the alpha greater than 1. So if alpha greater than 1, writing is 1. Okay, so alpha, this imply alpha greater than 1 means alpha minus 1 would be greater 0. Okay, right. Alpha since alpha greater than 1, this automatically imply alpha minus 1 will be greater 0. Okay, now from this inequality, divide by x minus. I am dividing both sides by mod x minus y, mod x minus y. So this part become on the mod. Okay, so this will be less than m into mod into x minus y whole to power alpha minus 1, right? This is positive and this is mod, so this part is always greater than 0, right? For all x not equal to y, because here denominator x minus y, okay, belongs to r. Now what we do, we take limit. Okay, because x not equal to y, so we can take limit x tends to y. Now I'm taking limit as x tends to y, right? What we get, see, this part is positive and this is positive constant. If you take limit x tends to y, then right side becomes 0 and right side become a positive constant into 0. This becomes 0, right hand side becomes 0. Also left hand side becomes 0. So by Synthesis theorem, left hand side 0, right hand side 0. So this part should be goes to 0. Okay, and mid part should be goes to 0. So I am writing that. It's trivial, na? 0 less equal to this, and if you take limit, because limit of this 0 will be 0, and this part limit will be 0, because m is positive and mod x minus y, this goes to 0. Yes, power is positive. Okay, if power is negative, then we don't say it goes to 0. This is power is positive, so if you take limit x tends to y, then this part also always goes to 0. Okay, so this goes to 0, this goes to 0. The 0 less equal to this, less equal to 0 means this part goes to 0. Okay, mod of x minus y, mod this part equal to 0. Okay, this part is 0, but we know that modular function is continuous. Okay, so limit goes inside, limit will go inside. See what happens if limit go inside the mod, limit goes inside the mod, then what we get, limit x tends to 0, sorry, x tends to 0, x tends to y, limit x tends to y, fx minus fy by x minus y upon x minus y. Okay, this will be 0. Okay, for all x not equal to y belongs to r. Okay, and this is the definition of differentiability. Limit x tends to c, fs minus fc by x minus c. This is known as f dash c, so this will be f dash y. F dash y equal to 0. Now see, derivative f dash y equal to 0, derivative is 0 where for all x r, and the domain is connected, r is connected. Okay, if a function has derivative 0 in a connected domain, so this must imply f is constant, identical equal to constant, and f is a constant function. So what you get, if f is a whole constant function with alpha exponent equal greater than 1, whole constant function with exponent greater than 1, then the function become constant. The only function satisfying whole continuous with exponent alpha greater than 1, the constant function. Okay, so for non-constant function, we must have alpha should be, exponent should be 0 less than alpha less equal to 1, always less equal to 1. Exponent is always greater than 0 and alpha should be less than 1 for a non-constant function. Okay, because if alpha greater than 1, using this proof we can say that f become constant. Okay, so see next. Now what is the definition? Mod fx minus fy should be less than m into x minus y whole to alpha. Okay, for xy belongs to R. I'm writing is when alpha less than 1, because if alpha greater than 1, then this function become constant. Okay, and constant function, for constant function is trivially satisfied. Okay, for constant function this will be trivially satisfied. Okay, see, alpha should be less equal to 1. Okay, right? So alpha may be 1. So if when alpha is 1, maybe alpha is 1, so this inequality gives, what do we give? From here we get mod fx minus fy will be less than m into x minus y. And this is nothing but Lipschitz continuity function. Okay, condition Lipschitz continuity. This condition ensure that f is Lipschitz continuous on R. Okay, so we can say that Lipschitz continuous is, if a function is Holder continuous, then we can say that it is Lipschitz continuous also for alpha equal to 1. Okay, so if we write in set inclusion, we can say that Lipschitz continuous containing Holder continuous. Okay, because Holder continuous, if function is Lipschitz continuous, then alpha should be 1, and in Holder continuous alpha should be 0 less than alpha less equal to 1. Okay, so in here is alpha maybe more, not only 1, maybe more, but here alpha equal to 1 only. So Lipschitz continuous is Holder continuous is the best condition or best result, you can say, then Lipschitz continuous. Okay, next we are going to solve the 3 question. I have tell the definition of Lipschitz Holder continuous. Okay, if it's minus alpha less than c into mod alpha, where alpha should be 0 less than alpha less equal to 1 and x equal to domain of, and for alpha equal to 1 we say that f is Lipschitz continuous. Okay, now so we are solving to go to solve this question. F is equal to root x is Holder continuous with exponent alpha equal to half on close 0 comma infinity. Okay, we are now solving this question number A. F is equal to root x. Okay, this belongs to close 0 comma infinity. See, so what we can do, we have to calculate this part. Okay, this part can be, if we can make this part less than sum m positive into mod exponential alpha sum alpha positive alpha, then we can say that this function become Holder continuous. Okay, so f is minus phi, this is what, root x minus root y, right? Now I can write this root x minus root y, root x up down I am taking is plus. Okay, positive. So you create just this by lower part. So I measure this. If we cut this, then this part came. Okay, now a plus b into a minus b. This means a minus b square. The upper part become x minus y by root x plus root y. Okay, I'm erasing. So what do you get? So we get mod x minus y is upper part, this lower part is root x plus root y, because xy belongs to close 0 comma infinity, right? So x will be greater than 0, y also greater than 0, so root x also greater than 0, it's greater than 0, so its mod will be itself. Okay, now so I get f s minus fy mod equal to this. Okay, now I can write this like this. I'm writing like this. If I take this in problem, because if it take out the square, then itself becomes, okay, lower part is root x plus root y. I'm taking one inside and other is outside. I can write this. Okay, Now this part will be always less equal to 1. Okay, now you may ask why this part is less equal to 1. This part is less equal to 1. Okay, see how this part is less equal to 1. I'm telling that root under mod x minus y will be always less equal to root x plus root y for all x y belongs to x equal to 0. Okay, this inverted always less than always hold. Suppose if you put x equal to 1 and y equal to 0, what do you get? 1 minus 0 1 1 0. So this part is equal to hold. Okay, suppose if you put x equal to 4 and y equal to 1, what do you get? In left part 4 minus 3 the mod means root 3. Right hand side part root 4 2 plus 1. Okay, 2 plus means 3. So right hand side will be 3 and left hand side will be 1.3 means 1.732. So this part will be less than. Okay, so if you put any xy, you always get less equal to this. So if it is less than this and this also positive, for this to positive. Okay, so if I divide this, so root under mod x minus y by root x plus root I will be less equal to 1. So I am using this less equal to 1. Root under mod x by root x plus root I will be less equal to 1. Okay, this part is equal to this, divide this by this, so you get root under mod x minus y by root x plus root I will be less equal to 1. Okay, I am using this in here, so we get root under mod x minus y. Okay, so f is minus y will be less equal to root under mod x minus y. Okay, so I am writing this clearly. What we get? So we get for the function f is equal to root x, x belongs to x equal to 0, fx minus fy the mod will be less equal to 1 to x minus y the root. This also going to be write like this, 1 into mod x minus y whole to alpha is half. Okay, so fx minus fy will be m, here m is 1, m1 is greater 0, so fx minus fy will be m into mod x minus y whole to alpha, and alpha is half, so alpha greater 0. Okay, and alpha is less than 1 for all xy belongs to domain of f. R is domain of f. Domain of f. So from here can you say this, that f is whole continuous with exponent alpha equal to what, half, greater 0. Okay, so f is called function is a whole continuous function with exponent alpha equal to half. Okay, on where, on 0 comma infinity, close 0 open infinity, because x is greater than 0. Okay, x is greater than 0 or less than infinity, x greater than less than infinity means x belongs to close 0 comma infinity. Okay. So if is root x is a whole continuous function on close 0 comma infinity. Okay, now so I've proved this. Now in the second result there is one more result. If one f2 are whole continuous function with exponent alpha, then the sum is also whole continuous with exponent same exponent. Okay, before going to prove this, we are going to this third part. This is more interesting. Okay, every whole continuous function is infinite. Okay, so what is say? C says that every whole continuous function is UC, uniformly continuous. Okay, every whole continuous function is uniformly continuous. How prove that? See, suppose we have a whole continuous function. F is a function from R to R. Suppose f is a function from R to R, which is whole continuous. Okay, so what you can write this from here? We write this, there is a m greater 0, positive constant greater 0, such that what happen? Mod fx minus fy mod less than m into x minus y whole to power alpha for all x y belongs to domain of f. where alpha is greater than 0 and less equal to 1. Okay, now we have to prove this. What to prove? We have to prove function is infiniteness. So we have to prove for any xy less than mod x minus y less than delta, we have to prove mod x minus y less than epsilon. Okay, so see, from here we can write, I have to search delta. Okay, I have to search delta where delta is independent of x and y. So how you search delta? First of all, write this. I have to make, if you prove, if you have to prove f is infiniteness, then you have to make f is minus y less than epsilon. Okay, so we have to make mod x minus y whole to alpha should be less than epsilon by m. Okay, so we have to make mod x minus y will be less than epsilon by m whole to power 1 upon alpha. Okay, let's see this part is independent of xy. Okay, so I can take this delta, and this part is also positive because m positive, epsilon positive, or each part alpha positive, 1 upon alpha is positive, so this part is positive, and it is independent of x comma y. Okay, so I can take this delta. To take delta equal to epsilon by m whole to root under 1 by alpha. Okay, so you get automatically get mod x minus y less delta. Okay, and this also satisfied x minus y less than epsilon. Okay, so what do you get? So if x comma y belongs to domain of f, okay, xy belongs to domain of f. So if x comma y belongs to domain of f with mod x minus y less delta, where delta is epsilon by m whole to 1 by alpha. Okay, this delta is depend only epsilon, not only xy. This delta is depend only on epsilon. Okay, this delta never depend on xy because there is no xy. Okay, so we can use this to prove infiniteness. Okay, if this delta is depend on xy, then we cannot say that the function is infiniteness. Okay, using this delta. So if I choose delta equal to epsilon by m root under 1 by alpha, 1 upon alpha. Okay, delta is positive, this is obviously positive, then we have mod fx minus fy less than equal to what if the whole coordinates, then this whole. Okay, now if x minus y less than delta, then mod x minus alpha whole to power less than delta to alpha. Okay, so less than mod x minus y, this can be made delta to alpha. Okay, so m, what is delta? Epsilon by m whole to power 1 over alpha, power alpha cancel, so this become m into epsilon. Okay, m cancel, this less than epsilon. So what do you get? If you choose delta equal to epsilon by m whole to alpha, where delta is positive, then f minus y will be less than epsilon. And this delta is depend only epsilon, not on xy. Okay, so for any xy equals to domain of f with x minus y less delta, where delta is epsilon by m root under 1 by alpha, and this delta is depend only epsilon, not only x and y, we get f is minus fy less than epsilon. So it is not the condition of uniformity. Okay, it is a condition of uniformity. From here we easily can say that f is uc on R. Okay, f is uc on R. So what we prove that? We prove if a function is homogeneous, then it is automatically inhomogeneous. So still now I have proved 3 results. First, watch, if function is Lipschitz continuous, then this contain in Holder continuous. Okay. Next I prove in C part, I prove in question C, I prove if function is Lipschitz continuous, then it came from Holder continuous. Okay, means Holder continuous gives Lipschitz continuous. And I now prove that if function is Holder continuous, then it is inhomogeneous. You see, means inhomogeneous of a function is the most best property than Holder continuous, and Holder continuous is most best property than Lipschitz continuous. Okay, because inhomogeneous, because Holder continuous, from Holder continuous we get inhomogeneous. Okay, and if we had Holder continuous, then we can say that function is Lipschitz continuous. by choosing alpha equal exponent equal to 1. Okay, so now going to solve a question of Nbhm PhD. Okay, 2015. What is the question? This question is about the condition of Holder-Condition function. Okay, using Holder-Condition function we can prove this. If it is a function from R to R, we solve this body hold. Mod f is minus less than root x minus root for less than R. Then this implies f is constant. Okay, so I am going to prove this. Given that solution mod f is minus fy less than mod x minus y root for x belongs to R. Okay, I'm this true for this given. Okay, this condition is given. This condition is given. If it's function, this is I have to prove f is constant. This function is constant. Okay, from here I have to prove f is constant. Means using this condition we have to prove f is constant. So how we will proceed? Take for all x y not equal to y. I am taking x not equal to y. Okay, and take y equal to c. C be any real number. Okay, then what happen? F is minus fc will be less than mod x minus c whole to power root 2. Okay, now I am dividing by mod x minus c both sides, so I get f is minus fc upon x minus c most less than x minus c root 2 minus 1. Okay, this mod is always greater than 0. Okay, now root 2 means 1.414. If I subtract from root 2 from 1, then this becomes 0.414. This is always positive. Okay, means root 2 minus 1 always positive. This power is positive. So if I take limit both sides x tends to c, this power is positive, and this extends to this goes to 0. So this term also goes to 0. So left side goes to 0, right side goes to 0. So in between middle term also goes to 0. Middle. Okay, so this part also goes to 0. So what I'm doing, taking limit, this goes to 0, this goes to 0. So in between, it is in between this, so it must goes to 0. And I have previously proved if mod goes to 0, mod of this quantity goes to 0, then this quantity also goes to 0. Okay, then I did light x tends to c mod fx minus fc x minus c, this is equal to 0. Okay, this is nothing but definition of f dash c. And what is the c? C y equal to c, or c be any real number. C be any real number. Okay, so if derivative is 0 for x belongs to for c belongs to R, means f is constant. Okay, if a function is derivative 0 with connected domain, if function derivative is connected domain, R is connected. Okay, right, R is connected. If function derivative 0 with connected domain, then this implies this function is constant. So the function becomes constant. Proof. I prove this. Okay, but f is constant, and I prove. Okay, so the proof is done. The f is minus less than x minus root 2, x minus whole to root 2 with 4 less than, then this implies f is constant. So root 2 is greater than 1. Okay, I am previously told if f is minus less than m into m, here m is 1. If I less than m into mod is equal to alpha, where alpha is greater than 1, then this function becomes constant. So it becomes constant. Okay, using the Holder continuous function of the property, we can easily say this. Okay, or otherwise you can prove this like this. Okay, now I'm going to take last result. I'm going to prove last result. What is the last result? Last result is this. If I found two function both have Holder continuous, both are Holder continuous with exponent alpha, then the sum also Holder continuous. Okay, so I am proving this in short. See, suppose f1 f2 are both Holder continuous with exponent alpha, get a 0. Okay, so what you get from there, you can write that there is constant mn get a 0 such that I can write it like this: f1x minus f1y less than m into mod x minus y whole to alpha, right? And For f2, similarly we can write this f2x minus f2y, this can be made less than n into mod x minus y whole to alpha. Okay, for all xy belongs to R, right? Now I am naming it 2. I have to prove the sum f1 plus f2 is holographic, okay, with exponent root alpha, exponent alpha. So I am starting it like this. Take, I have to prove the sum is holographic, okay, right? So take g equal to f1 plus f2 and proceed with g x minus gy. Okay, I have to calculate this. This should be made less than some positive constant, say c into mod x minus y whole to alpha. Okay, I have to prove this. So I prove this. So I see what I meant. What is g? f1 plus f2. Okay, x. What is g? f1 plus f2 y. Okay, so this can be write f1x plus f2x. This can be write f1y minus f2y, right? So take this with this, and this second, first with third, and second third, second fourth. So you get f1x minus f1y, f2x minus f2y. Okay, let's see. See what you get: gx minus gy. I'm combining this f1x minus f1y, f2x minus f2y. Now you have a triangle variety, mod a plus b. This is equal to mod a plus mod b. So you get mod f1x minus f1y. This mod will less than f2x minus f2y. Now f1 is holographic, so this part can be made less than m into x minus y whole to alpha. Okay, and f2 is holographic, so this part can be made less than some n into x minus y whole to alpha, right? Because f1 and f2 are both holographic, so f1 minus f1x minus f1y can be made m into x minus y whole to alpha, and this plus, and f2 is also holographic, so this can be made f2 x minus f2y can be made less than n into x minus y whole to alpha. Then you can write m plus n x minus y whole to alpha. Okay, take m plus n equals c, and because m is positive, n is positive, the sum is always positive, so we get a constant c such that gx minus gy L is equal to c into mod x minus y equal to alpha. So this ensure that the function g is holographic, okay, with exponent alpha greater 0. Okay, and what is g? G was f1 plus f2, so f1 plus f2 become holographic. Okay, so I prove that if function f1 and f2 are holographic with constant with exponent alpha greater 0, their sum f1 plus f2 is also holographic. Okay, so this is the last continuous question. So I have discussed the topic in details. Okay, there is one more property in holographic function. This property I'll make a video in separate video with this property. That property was if the function f absolute continuous with f dash belongs to LP close AB. Okay, then this implies f is holographic on close AB. This property I will prove in the next video. Okay, so thank you. Okay.